and welcome to the Mathematicians Podcast. I'm your host, Benjamin Cornish, and today we are slicing into the world of ancient Greece to explore the life and legacy of Menaechmus, one of the lesser celebrated yet profoundly influential mathematicians of antiquity. His work forms the basis of some of the most important branches of mathematics today, including geometry and algebra. So grab your notebooks and sharpen your pencils. This episode is packed with mathematical revelations and a touch of ancient intrigue. In each of my scripts, I segment the themes of the story I tell with little titles, and the first always reads Intro Ramble. Well, today I would like to tell you about one of my actual rambles. There's something about the thrill of uncovering something ancient, something buried for millions of years, and that's what makes fossil hunting a little addictive. It's the anticipation, the slow and patient search, the moment when you pick up an ordinary-looking rock, turn it over, and realise there might be something groundbreaking just beneath the surface. A few years ago, I found myself on one of these trips, trekking across the windswept cliffs of Lyme Regis on England's Jurassic south coast, about an hour from where I live. If you've never been there, picture towering cliffs with the ocean biting at their base, every wave chipping away at the past, revealing fragments of history. It's a place where time feels tangible, where layers of rock hold the imprints of creatures that swam in ancient seas long before humans ever dreamed of numbers or geometry. It also harbours a very impressive Roman sea wall made from an early form of concrete. That morning, I was armed with my hammer, a chisel, and an old canvas bag that had seen better days. I spent hours scouring the ground, occasionally prying up a loose rock, hoping for the telltale spiral of an ammonite or the delicate outline of a fossilised fish. And then I stumbled upon something that didn't quite fit. At first glance, it was just a lump of dull grey stone, rock solid, but unremarkable in every way. Although something about its weight, the way it felt in my hand, denser, heavier than it should have been, made me dig a little deeper. I turned it over, inspected its rough surface. Nothing, just an ordinary rock, the kind you'd take for granite. But still, something about it caught my attention. I took out my hammer, lined up the chisel, and struck it clean in the centre. The crack rang out against the surrounding cliffs, and the rock split in twain. And that's when I saw it. The inside was unlike anything I'd expected. A glistening crystalline heart, deep violet and shimmering with light. A geode hidden beneath the plain, lifeless exterior. A perfect secret, waiting to be revealed. The outer shell had given no clue as to the marvel inside. It was only by breaking it open, by fracturing the surface, that its true beauty was revealed. And that, my friends, is how mathematics works. Because sometimes problems look impossible from the outside. Take the ancient Greeks, struggling to solve a puzzle set down by the gods themselves, the Delian problem, the challenge of doubling the volume of a cube. For years they chipped away at the problem, searching for a solution within the constraints of simple geometry. It wasn't until Menaechmus took his hammer, his mathematical mind, and cracked open the world of conic sections that the hidden answers were finally revealed. So today, we're taking a journey into the mind of a man who saw beneath the surface, who carved through mathematical stone and unearthed something extraordinary. Menaechmus lived in the 4th century BCE, allegedly a pupil of Eudoxus of Cnidus, who we discussed in episode 13. Eudoxus was a brilliant mathematician and astronomer who developed the method of exhaustion, a precursor to integral calculus. Although we should always be a little cautious of so-and-so being a pupil of such and such. It's a little romantic, but not always factual. The ancients had a particular preclusion to assuming a continuous lineage of teacher to student, and to be honest, I enjoy it too. Born in Alepicanessus, a small town in ancient Greece, Menaechmus grew up in an intellectual environment that prized reason and discovery. He was likely influenced by the Pythagoreans, whose ideas about geometry and the harmony of numbers were a significant part of the intellectual fabric of the day. Unfortunately, personal details about Menaechmus are sparse, as is often the case with ancient figures. However, there are a few tantalising anecdotes. According to one story, Menaechmus was a friend and tutor to Alexander the Great. Legend has it that Alexander, impatient and brimming with youthful arrogance, demanded a shortcut to understanding geometry, and Menaechmus replied, "There is no royal road to geometry." This pithy remark not only underscores Menaechmus's dedication to rigorous learning, but also serves as a timeless reminder that mastery requires effort. Now, let's talk about Menaechmus's mathematical contributions, starting with his work on conic sections. If you're not familiar with conic sections, they are the curves obtained by intersecting a cone with a plane. Depending on the angle and position of the intersection, you can get one of three distinct shapes: ellipses, parabolas, or hyperbolas. Remembering here that a circle is a type of ellipse. No, I did not forget it. Nowadays, we would discuss a conic section using algebra, in a branch of geometry called, wait for it, algebraic geometry. In this sense, we would use an equation of x and y to describe the curves as a collection of points, where the x and y represent the perpendicular measures in the horizontal and vertical direction. And yes, this is just a coordinate grid with a graph on it. Although algebraic geometry is not limited to such a specific case. In my teaching at A-level, we tend to use the notation of a parabola as y squared equals 4ax, where a represents the focus. More on that later. Those of you who like to listen along with desmos.com open at all times will notice that this is a parabola or quadratic curve, but pointing to the right instead of up. Wouldn't it be fun if we could redefine this using methods that were available to Menaechmus at the time? Oh, go on then. Consider a right circular cone. That is a cone where the line from the vertex to the centre of the base is at a right angle to the base, and the base is a circle. Let us also consider the vertex to be a right angle. That is, the angle between the edge and the vertical is 45 degrees. Let us call the vertex A and the diameter of the base BC. If we find a point on the side of the cone, called P, then we can slice a circle at P that is parallel with the base, a horizontal circle. On this circle, we note the diameter RV, such that RV is parallel with BC, and they are collinear points ARB and AVC. So in other words, RV and B is directly on top of BC, just further up the cone. We can then also slice through P at an angle parallel to the line ARB, that is 45 degrees to the vertical. This diagonal slice shall form our parabola. The parabolic slice will intersect with the circle PVR at another point called Q, making a line PQ which will intersect RV at the point O. Notice that by symmetry we have a perpendicular lines PQ and RV. And now, given that RPV is a semicircle and OP is perpendicular to the diameter, we have the length OP as the mean proportional of RO and OV. In modern language, we would call it the geometric mean. Essentially, we have the calculation that OP squared is equal to RO times OV. Now, consider the intersection of the parabola with the line AVC. This will intersect at the point D, where D will also be the highest point on the parabola, often called the vertex. We can see that there are two right-angle isosceles triangles that are similar, that's ABC and DOV. Thus, we can form the following ratio: OV over DO is equal to BC over AB, and we should also find the corresponding point on ARB called E, such that ED is horizontal. Therefore, again, by similar triangles, we can say that RO is equal to ED, and therefore we can say that there is the ratio ED over AE is equal to BC over AB. I now wish to compare the relationship between the lengths OD and OP. For the sake of ease, I shall refer to OP as Y and OD as X, although we note that this is an anachronism. So we can now say that Y squared is RO times OV. Substituting the OV with the first ratio, we have Y squared is RO times DO times BC divided by AB. Substituting RO with ED and the second ratio, we have Y squared is equal to BC squared times AE times DO divided by AB squared. And here we can see that DO is X, but also the lengths BC, AB and AE do not depend on where P is located. They are all constants, and therefore we can replace them with a single value, maybe K, and thus we have Y squared is equal to Kx. Now, I hope you can follow along with your own diagram at home, or at least you enjoyed this talk of ABOP, ETC as an example of ASMR, although there is a risk it left some of you feeling DFQ, perhaps only truly enjoyed by the OGs. Menaechmus is credited with discovering these curves, and he did so in the context of solving one of the great mathematical challenges of his day, the problem of duplicating the cube. The task, also known as the Delian problem, required constructing a cube with twice the volume of a given cube. This wasn't just an idle puzzle. Legend has it that the Oracle of Delphi posed the challenge to the people of Delos as a way to end a plague. The better legend is that after requiring a cubic altar of twice their magnitude, the acolytes returned with an altar where every length had been doubled, and they were then sent back to have another try, as this volume was 8 times the size. The history of maths is analogous to noticing the same misunderstandings that modern students still have. Solving the Delian problem, then. Menaechmus approached the problem geometrically, using conic sections. He demonstrated that the solution could be found by intersecting two parabolas, or a parabola and a hyperbola. Let me break that down. He started with the equations of two parabolas, and for the sake of ease, I will say these in algebraic terms. X squared is equal to a times y, and the other curve being y squared is equal to b times x. At this point, you might want to go over to desmos.com and try plotting these two curves yourself. Again, I'm going to stick with the algebra, otherwise we'll be here for hours. So if we plot these on a graph, we notice that they point in perpendicular directions. So this is analogous to slicing the cone into perpendicular cuts. But watch what happens when we solve the equations simultaneously. That is, when we find the points of intersection. Naturally, they both intersect at 0, 0, but the second solution can be found by substituting one equation into the other. So rather than x squared is equal to a times y, we can replace that y with the y from y squared equals bx, and that's going to leave us with x squared is equal to a times the square root of bx. Now, we don't like square roots, so let's try squaring both sides, and we get x to the power of 4 is equal to a squared b times x. Well, if we solve now for x, we can divide through, and we get x cubed is equal to a squared b, remembering that a and b are both constants, so a squared b is a constant. But then we can take a cube root, so we get x is equal to the cube root of a squared b. Well, if we let maybe a equal 1 and b equal 2, then we have found a length that is equal to the cube root of 2. And therefore, Menaechmus was able to derive the length of the side of a cube that would have doubled the volume of the original. Now, this was a monumental achievement for its time. Although his solution required tools that went beyond the constraints of pure geometric construction, rulers and compasses, it threw down the gauntlet for later developments in algebra and analytic geometry. In fact, it's not a stretch to say that Menaechmus drew the grid for Descartes, who would formalize analytic geometry almost 2,000 years later. While Menaechmus' solution was innovative, it wasn't the only approach. Archytas of Tarentum, another brilliant mathematician and philosopher of the time, proposed a different solution to the Delian problem, Archytas used three-dimensional geometric constructions involving the intersection of a torus, a cylinder, and a cone. This approach was more aligned with the Greek tradition of using purely geometric tools, but still cheated by using 3 dimensions. Now, the rivalry between Menaechmus and Archytas, though not documented in dramatic detail, likely reflects the broader intellectual debates of the time. Archytas, as a Pythagorean, emphasised strict geometric construction, while Menaechmus' use of conic sections hinted at the beginnings of a more analytical approach to geometry. Their differing methods highlighted a pivotal moment in mathematical history, a crossroads between classical geometry and the seeds of algebra. So let's pause here to appreciate just how revolutionary the discovery of conic sections was. These curves aren't just abstract mathematical entities, they're everywhere. Ellipses describe planetary orbits, parabolas govern the paths of projectiles, hyperbolas show up in the design of telescopes, and even in the behaviour of light waves. Menaechmus didn't know it at the time, but his work would become essential to the fields of astronomy, physics, engineering. I could go on. Menaechmus' intellectual journey was closely tied to Plato's Academy, one of the most famous centres of learning in ancient Greece. While there's no direct evidence that Menaechmus was a formal member of the Academy, his work aligns closely with the Platonic emphasis on geometry as a means of understanding the universe. In fact, it's said that Menaechmus' studies were inspired by Plato's belief that geometry was the purest form of knowledge, a kind of divine language that could reveal the secrets of existence. Interestingly, Menaechmus also dabbled in other areas of knowledge. Some accounts suggest that he made contributions to astronomy, though details are scarce. Given his geometric prowess, it's likely that he applied his skills to celestial problems, perhaps working on the models of planetary motions or refining the Greek understanding of the cosmos. At this stage in the podcast, I should take a moment to reflect on my own methods of historiography. So far, I've spoken little about astronomy as a legitimate mathematical pursuit. I've even dismissed it as applied counting. However, with the curves of Menaechmus now in our tool belt, in particular the discovery of the ellipse, it's now within reach for mathematicians to make accurate models of the planets. That is not to say that they will, only that it is possible. Any modern astronomy undergrad will tell you that the objects in gravitational orbit actually do follow elliptical trajectories. And of course, any astronomy professor will tell you actually it's not that simple, but it's a good place to start. Therefore, from now on, I will try to take a more grown-up stance on astronomy. Perhaps we could borrow the definition from Archytas of what would become the quadrivium. Arithmetic is static number and ratio, harmonics is number and ratio in movement, geometry is static shape, and astronomy is shape in movement. So what can we learn from Menaechmus today? For one, his life reminds us of the enduring power of curiosity and intellectual rigour. He tackled problems not just for their practical implications, but for the sheer joy of discovery. And in doing so, he expanded the boundaries of human knowledge. In the mathematical world, we tend to divide those that push the boundaries as professional mathematicians and recreational mathematicians. But in truth, we're all just doing it for fun. Before we wrap up, let's take a moment to reflect on the beauty of the conic sections. They're a perfect example of how something as abstract as mathematics can have profound, real-world applications. And it all started with Menaechmus, a mathematician who dared to explore the unknown. Well, thank you for joining me on this journey through the life and work of Menaechmus. If you enjoyed this episode, don't forget to subscribe and leave a review, and share it with your fellow maths enthusiasts. Or join me on Blue Sky at mathematicians-pod. Next week, we will be looking at Thymaridus, who was simultaneously brilliant and intriguing. You'd be blooming furious to miss out on the Mathematicians podcast. Until then, goodbye. The music today is Danse Macabre Finale by Kevin MacLeod. You can find more information in the show notes.